Hey, this is class number 24, and we're going to look at finances, savings for retirement. And it's not a section in your book, it goes with the packets. There are a couple pages of reading that precede this page. All right, so our daily summary. In this lesson, we're going to explore fixed annuities, including saving for cars, houses, and retirement. In our demo section, we're going to look at Mary. Mary is saving up for a car, and she invests $200 per month. So notice right off the bat, this is not one lump sum. So this is how it's different than what we've looked at before. All right, so she's going to invest $200 per month in an account paying 6% annual interest that gets compounded monthly. So there's two questions below. One is easy and one is hard. Right? The first one, how much money is she going to have invested in 3 years? Well, she's doing $200 per month. So 200 times 12 will tell me how much she does each year. And then times it by 3 will tell me how much over the 3 years. And it turns out she's going to end up investing $7,200 altogether during those 3 years. Second question is a tougher one. So we've got to look at that first month where she puts in $200. So she's going to get $200 as a principal. Then we've got to times it by 1 plus 0.06 divided by 12, because remember it's being compounded monthly. And that's going to sit in her account for 36 months. So it's going to get compounded 36 times. And then we have to do that for the second month. And notice that if we think about the $200 that puts in the second month, same interest rate, still compounded monthly, but now it's just going to be in there for 35 months. And here's the problem. We have to think about each month separately, all the way down to that last payment of $200. And this last payment isn't going to earn any interest. And the reason for that, we'll see later, is to make a formula to simplify this a little easier. So last payment, again, gets no interest. All right, so again, we're assuming that for the formula that we're going to see below. So again, the problem is that first payment grows for 36 months, or accumulates interest for 36 months. The second payment, she puts that in the next month, so it's only going to grow for 35 months. And again, every payment after that is going to be one less month than the payment before that. So it's not as straightforward as what we saw in earlier sections. All right, so from your book, a fixed annuity is a sequence of equal payments made or received over regular, can be monthly, quarterly, or annually, time intervals. You may be making regular deposits to save for a car, a vacation, a wedding, or college, or you may be making regular payments on a car loan or home mortgage. You could also be at the receiving end of an annuity, which means you're getting regular payments from an inheritance or a lottery jackpot. All right, so here's the formula for fixed annuities. All right, the future value F of a fixed deferred annuity consisting of N payments of M dollars per year for T years, having an annual percentage rate of R%, and the R is written as a decimal, is given below. So again, here's that future value. So future value F. Okay, we've got our monthly payments or monthly investments. And payments we can be putting into an account that earns money. And then in here we've got R over N. So R is your interest rate, or APR, and it should be in decimal form. N is going to be the number of payments per year. So if you're doing monthly payments, N would be 12. And then T is the number of years. Okay, and similar to what we saw before, I just want to call your attention to a slightly different version of this formula that you may see in your textbook or the reading that preceded this. And what it does is, again, replace R over N with lowercase p and N times T with capital T. So it looks like a nicer way to write the formula, but it's maybe a little bit more difficult to use because you have to remember that in this case, lowercase p is R over N, it's that periodic interest rate, and capital T is the total number of payments. Let me put total in here just to remind you. Okay. All right, so note that n equals 12 if we make monthly payments, but in general, the periodic interest rate is R divided by the number of payments per year. So for instance, if you're making 2 payments per year, we would write R over 2. All right, so number 5, now we can tackle the question about Mary and her car. So Mary invests $200 per month in an account paying 6% annual interest, compounded monthly. So how much money is she going to have in 3 years? So we're interested in the future value, so F is going to be our variable. We know that she puts in $200 per month, so that's our M. And then we have that constant 1 in the top. Our interest rate is 6%, so it's 0.06 in decimal form. N remembers the number of payments per year, and she's doing this monthly. Let's see, per month. So we're going to divide that by 12. And then we're doing this 12 times per year for a total of 3 years. Here's our 3 years. Minus 1, that's another constant. That's going to be in there every time you use the formula. And then we need to do R divided by N in the bottom. All right, so similar to our last class, the biggest challenge here is often getting this to work on your calculator. So as much as possible, you want to do all of this together before you press enter. So trying to enter it is one step. If you're doing that, I'll give you a hint, you're going to need parentheses to keep that top part of your expression together and an added set of parentheses to keep that bottom part of your expression together. And what I'll do is I'll give you the answer to this. You should get $7,867.22. But you should press pause and see if you can figure out how to get to that value. And getting close is a good first step, but then you want to see if you can get it to the exact value. Right, so as an aside, we know how much money she's going to have in 3 years. Let's see how much interest got earned. So I know this question isn't asked for, but how much interest did she earn? I guess I should put ED on the end of that. So interest earned. All right, well, remember she put in $7,200. So if we subtract that from what she has after the 3 years, we're going to get a difference of $667.22. So this is the amount of interest that she made by putting all that money into her account every month for 3 years. So again, that's the interest earned. And this right here, just as a reminder, that was the total over 3 years of payments. Okay, so just as a reminder, you do have that formula sheet in your packet, and we're looking at this first column, multiple investments made at regular intervals. So this is that formula we just looked at. All right, so in number 6, Mary has her heart set on a car that costs $10,000. How much more would she need to invest each month so that she could afford the car of her dreams? Well, notice we now have the goal. So we have our future value. So we're going to put that on the left side of the equation for F. But we don't know how much she should put in each month. So we need to leave M in as our variable. So up on the top, see, she's doing the 6% interest she had before. She's doing that monthly for 3 years. And then in the bottom, we're going to have 0.06, again, split up into 12 pieces. So our goal here, again, is to get M by itself. So we're going to divide both sides by this expression on the right. So to get M in one step, we need to take 10,000 and divide it by this expression. And again, your goal is to be able to do this in one step. So I'll put a couple more parentheses in there to help you get started. All right, so if you're typing this in, you want to do 10,000 divided by, and you're going to keep this set of brackets or parentheses in there. But you're also going to want to include 1 to keep the top together and 1 to keep the bottom together. All right, so when you do that, and again, press pause, double check this, make sure you get your calculator to work for you. You should get that her monthly payment should be $254.20. So in other words, she's going to have to put in another or an additional $54.22 per month. So if she wants that $10,000 car, she's got to spend or save another $54.22 per month. All right, number 7. Ian and Caitlin decided to begin saving for their retirements. They love teaching at GCC, but they don't want to work here forever. So they each open up a Roth IRA. This is a wonderful investment vehicle where you're allowed to invest up to $5,500 per year, and you don't pay taxes on the gains that your money makes when you take it out at retirement age. The downside, though, is that once you put money into the Roth IRA, your money is basically locked up until you reach retirement age. In other words, if you want to use the money before you're in your 60s, you're going to have to pay steep penalties. All right, so we're going to assume that the IRAs that they invest in earn 7% interest per year, compounded annually. So on his 34th birthday, Ian deposits $2,000 into an IRA. And by the way, this stands for Individual Retirement Account. Okay, so again, IRA. On each of his 9 subsequent birthdays, he's going to make another $2,000 deposit, but then he's going to stop adding money to the account. So notice he's going to be making 10 deposits. One on his 34th birthday and then 9 following birthdays. All right, Caitlin follows a similar investment plan, but she started saving for retirement at age 22. So on her 22nd birthday, she also puts, she put in $1,000, half of what Ian put in. So she puts $1,000 into an IRA. Like Ian, she makes a total of 10 equal annual deposits, and then she stops adding money to the account. Okay, so the question is, how much money is each person going to have in their IRA when they retire on their 64th birthdays? So this is a tough question. If Ian and Caitlin made investments all the way up until they retire, then they'd be involved in an annuity, and we could simply use the formula that we've been using all class. Since they stopped investing but continue to let the money grow, we'll have to answer this question in 2 steps. So first step, we're going to figure out how much money Ian and Caitlin have after their last deposit. And then step 2, we're going to pretend that Ian and Caitlin make 1 deposit into a new account after the 10 years of investing. And we'll figure out what these new accounts grow to at retirement age. All right, so in number 8, we're going to look at Ian's, and you're going to look at Caitlin's in the group activity today. So here's Ian's scenario again. On his 34th birthday, Ian deposits $2,000 into his IRA. On each of his 9 subsequent birthdays, he makes another $2,000 deposit, but then he stops adding money to the account. So we're going to assume that the IRA earns 7% interest per year, compounded annually. All right, so how much money will Ian have in his account the moment after he makes his last $2,000 deposit? So this is our step 1. So we're going to find the future value when Ian makes $2,000 payments, multiple payments or investments. And our interest rate is 0.07, but this is compounded annually. So if you want to think of it as 0.07 divided by 1, you can, or you can just leave out the 1 in the denominator. It does this 10 times. And on the bottom, we have our interest rate divided by n, which is just 1. It's the number of payments per year. Okay. And again, on your calculator, so if you can do this in 1 step, what you'll find is that Ian is going to have a total of $27,632.90 at the end of those payments. Okay, so he stops investing. So number 9, now suppose that he opens up a brand new account, which earns 7% interest per year, compounded annually still. So he's going to make this 1 deposit in this account in the amount of the answer to the previous question. So how much money will be in his account when Ian retires on his 64th birthday, assuming he makes no other deposits into the account? So step 2, we're going to go back and use this formula for compound interest. So remember, there's only 1 lump payment here, 1 lump investment, not multiple ones. All right, so we've got our formula for compound interest. And in this case, your future value is going to be equal to, and we're going to take this answer from here, we're going to plug it in for P. And then we're going to times that by 1 plus 0.07 over 1. And again, you can leave that 1 out if it makes more sense to you. 1 times 21. All right, so the first question is, where did the 21 come from? Remember, he started on his 34th birthday, and he did this for a total of 10 years. This means he stopped on his 43rd birthday. And now he's going to his 64th birthday. So this is a total of 21 years that he's going to let that money grow. All right, so next up, we want to calculate this. So what's our future value going to be? So at the end of those 21 years, those additional 21 years, he should have a total of $114,415.75. Oops, I already had my dollar sign there. And so you can press pause, try that calculation out. Make sure you can come up with that same value. And as I said before, you're going to check out what Caitlin's account will grow to in the group activity. And you'll see if there's any difference.